Welcome back to Unit 1 of our course, The New Perspective. We are now on Lecture 7. And our objective is to connect up this ballistic and diffusive conductance that we talked about in the last two lectures. So what we had shown was that starting from our general expression for conductance, you can obtain an expression for the ballistic conductance or this diffusive conductance by using this expression for the time. That the basic difference is in the ballistic limit, the time is proportional to the length. In the diffusive limit, the time is proportional to length squared. Now, the way you can get a general answer that would work for both limits and in between is to write the time as this L over V bar, the average velocity, plus L square over 2D. Now, it might look a little surprising how you're adding the two. See? So one way to justify it would be to say something like this, that you're writing the time kind of like a polynomial expansion. L, L square. In principle, there could have been an L cubed, etc. And of course, what you expect is then when the length is very small, then the first lowest power should dominate things. When the length is large, that's when the higher powers will dominate. And you could say, well, for very long things, I know the answer from the diffusive limit, that it's L square over 2D. And so that tells me that firstly, I shouldn't have L cubed, L fourth, etc. because we know that for long things, it goes as L square. That's from diffusion theory. And for short things, we know that it should go as proportional to length. So that tells us that the lowest power should be L. So that could be one way to justify this. If you accept that, then you could have rewritten it in this form. That is, this first term is the ballistic time. So I can pull that out. And so the second, what we have here is like the ratio of the diffusive time to the ballistic time. That's what we have written here, which you could rewrite in the form L over lambda, where this lambda is like the mean free path, as we'll show. But for the moment, we have just defined the lambda as the ratio of this diffusion coefficient to the average velocity, 2d over v. So if we accept this, then this is just a little algebraic rearrangement of things. So let me say a little more to justify why we might expect this. Why time, why the transfer time should be given by the ballistic time times this 1 plus L over lambda. Okay. Now, what we did in the last lecture, if you remember, when I was trying to justify this diffusive time, the way we did it is we said, well, let's just look at the electrons in the channel and relate it to the flux. And a fundamental relation that I've often brought up is that the average time an electron spends in the channel is equal to the number of electrons in the channel at steady state divided by the flux of electrons, the rate of flow of electrons, this current. Now, based on that, what we saw was that for ballistic transport, the amount of electrons that are stored in here was this d over 2. And interestingly, even in the diffusive limit, the answer is still the same, d over 2. The only difference is that in the first case, all the electrons are in the northbound channels, as I said, that you can think of this channel as having half the states that are northbound, the other half that are southbound. So it's like in the ballistic case, all northbound states are filled, all southbound states are empty. Whereas in the diffusive case, northbound and southbound are about equally filled, but the occupation goes down as you get from this end to this end. Right? Because electrons come in from here, and so there's lots of electrons at this end, but then as you go through the channel, you have less and less that are remaining, because many of them have turned around and gone back, right? So what happens in a situation that's kind of intermediate between the two? And this is something we'll talk more about in, as I said, in the third unit of this course, when we talk about this, what and where is the voltage. But for the moment, let me just give you a simple description, and that is, let's say T, we use this capital T to define this fraction of electrons that make it from source to drain. That is, in the ballistic case, any electron that came in from the source goes all the way to the drain. And that's why all the northbound lanes are completely filled all the way, steady state. Now let's assume that we have kind of semi-ballistic transport. So the electrons that come in from here, let's say 50% get through. So what that means is by the time you come out at this end, the northbound lanes have become kind of half filled, 50%, or 30% filled, or 70% filled. So that's this T. So in that case, when I try to plot the electron density, I'll see something like this. At this end is d over 2L, but then the occupation of electrons, as you go, occupation of in this number of electrons in the northbound lanes, that's this electrons per length per unit energy, will have gone from d over 2L down to T times d over 2L. And as far as the electrons going the other way is concerned, that will start out at 0 at this end, but will gradually build up. And the reason it builds up is, again, because electrons are turned around. And in Unit 3 of this course, we'll actually do this more quantitatively. We'll write down the proper differential equations. Okay. But this is what it would look like. And the first point I want to make is that if you look at the number of electrons that are in the channel, not surprisingly, the answer is still the same. You might have guessed that. After all, when it was ballistic, it was d over 2. When it's completely diffusive, it's d over 2. So when it's in between, it's probably still d over 2. And that's what you can get, actually, if you analyze this properly. How many electrons do you have in the southbound lanes? How many do you have in the northbound lanes? Add them up, you'd get exactly the same answer, d over 2. What's different now, what's different in all three cases, this, and this, is the current that is associated with it. The reason the times are all different is because the Q's are all the same, but the currents are different. So the current has the highest value in this case, corresponding to the shortest time. Here the current is relatively low, giving a longer time, and this is in between, you see. So if you try to write the current, what you might expect then is that whatever current you had in the ballistic case, now the current will be T times that, because only 50% of the electrons get through. So previously, if you had a ballistic current of, let's say, 2 milliamps, now you will have only 1 milliamp. So this current would be like T times that. Now what that means is, when I try to calculate the average time an electron spends in the channel, I'll get Q divided by I, and I is T times the ballistic current, and Q divided by the ballistic current is the ballistic time. Remember, the Q stays the same in all three cases, whether you are ballistic, whether you are diffusive, whether you are halfway there. All three cases, same Q. It's the I that's different. And so it's TB divided by T. Now, this transmission coefficient, this fraction of electrons that get from left to right, that's actually given by mean free path divided by length plus mean free path. In fact, one could use this almost as a definition for mean free path, because you could say that, well, when the length is really short compared to a mean free path, that's when I can drop this so that T is 1, which means 100% of all the cars, all the electrons get through for a short thing. When the length is approximately 1 mean free path, then you see, if I put L equal to lambda, I'll get a T of half. So you could say that, well, that's the way I'll define my mean free path. It's the length such that only 50% get through. Of course, you could have defined it as the length for which 30% get through, or a length for which 60% get through. Okay? And the conventional definition is not exactly this. We have chosen this definition because that way this expression comes out nicely. It's like lambda over L plus lambda. Whereas if you had chosen a different definition, you might have got, say, 1.5 lambda over L plus 1.5 lambda. So exactly how you define the mean free path, that somewhat can be different from one definition to the other. But And we'll, in the next lecture, we'll see what the exact expression for this mean free path is. Okay? But the bottom line is that this fraction of electrons that make it from source to drain can be written in this form, lambda over L plus lambda. And if you combine that with this, then what you get is that the time is equal to the ballistic time divided by T, and the divided by T means like L plus lambda over lambda, which can be written as 1 plus L over lambda. So this is the expression that I had mentioned earlier, that the time in the general case can be written in this form. When L is small, it's the ballistic time. When L is large, this is what will become the diffusive time. So if you now combine that, so for ballistic case, you see we had an expression for ballistic conductance that we obtained before by putting the ballistic time for T. But now let's say we use this one. So we have the time is ballistic time times that factor. So let's use that here. So what you'd get then is the conductance would be the ballistic conductance divided by that factor. Why? Because the T is in the denominator. So when I put a ballistic time there, I got this. Now I'll put something a little bigger. I'll put the ballistic time times that factor. So when I put that in, the conductance I'll get will be less by that same factor. So this is the expression you'd get, which you could rearrange to write as GB lambda over L plus lambda. And this is something you can then identify with this expression, conductivity times area over L plus lambda. So you have this expression for the conductance. Note that if I have a very long channel, then I can drop the lambda from here. And so the conductance will be sigma A over L, just like you learn in freshman physics, what it should be, Ohm's law for large conductors. That's what you'd get. But then, when length gets really short, the point is the resistance doesn't become zero, conductance doesn't become infinity, it tends to some constant value. See? And the thing to note then is that the sigma A you can identify with this GB times lambda. So usual understanding of conductivity, as I said, starts from large conductors. Whereas in this new perspective that we are using here, the fundamental thing you first look at is the ballistic conductance. That any material, first thing you ask is, if I made it really short, what conductance would I measure? That's this ballistic conductance. That's a material property. And now you ask the question, well, now if I make it long, what is the conductivity? Well, the answer is, take your ballistic conductance multiplied by the mean free path, and that will be this conductivity times area. So that now brings together all these concepts that we talked about. So it puts it all on the same page now. We had this expression for conductance, we looked at the ballistic limit, looked at the diffusive limit, and you could write it all together in this form where this conductivity is given by this GB lambda. I notice I've missed an area here. This should have been sigma A. Okay? So now what we'll do is, we are ready to move on to the next step, which is, we'll talk a little bit about these two quantities that appear in, one of these appears in the expression for the ballistic conductance, and the other appears in the expression for the conductivity. That's what we'll talk about in the next lecture. Thank you.